Let's look at this starred problem from Corman, problem number 3-7 from chapter 2. You are asked to describe the theta of n log n algorithm that, given a set S of n integers and another integer x, determines whether or not there exist two elements in S whose sum is exactly equal to x. So the input to the problem is a set S of n integers. Let's assume they are given to us in an array called S, indexed from 1 to n. And you're given another integer x, and you need to find out if there exist two elements in S which add up to x. So instead of searching for a given value in this array, you are asked to search for a pair of values in the array which add up to the given value. Now, a brute force way of approaching this problem is to ask how many pairs of integers are there in total which can be drawn from S. Okay, how many pairs of integers can we draw from this set S of n integers? Well, if you have to draw a pair of integers from the set S, the number of ways of doing that is equal to the number of ways of choosing two integers from a given set of n integers, and that's n choose 2, which is n times n minus 1 divided by 2. So a brute force algorithm would check every possible pair of integers drawn from the set S, and for each pair it would check whether the two integers add up to x or not. If they do add up to x, then you say yes and you terminate the algorithm at that point, if necessary outputting what those two integers are. And if not, you just iterate over all possible pairs of integers. And at the end, if you don't find even a single pair that adds up to x, you can declare that the answer is that there does not exist a pair. There does not exist such a pair which adds up to x. So this algorithm would have a double loop for I varying from 1 to n and from j varying from 1 to n. Um, you're going to check, of course you don't want to compare the same element with itself. So basically this I is helping you to fix what the first integer is. This j is helping you to fix what the second integer is. And by independently varying I and j, we are trying to create all possible pairs of integers. But a valid pair is one where you're not choosing the same element twice. So you'll just say that if I is equal to j, you'll just continue. This means you'll just immediately exit the body of this loop and iterate over the next possible combination of I comma j. You don't want to use the same value. You don't want to pick the same element twice. So pairs where you are picking the same element twice is such pairs are not to be considered. So assuming that I is not equal to j, if s of I plus s of j, if the two integers add up to x, then you return whatever. You can return true, or you can return what the values of these two integers are. You return some answer. And if at the end of this loop you exit the loop without returning in the middle, you'll return not found. So I'm using the indentation here to delimit blocks. So this is the body of the uh, this is the body of the inner loop. From these two statements are within the body of this inner loop, and this return not found is placed after the end of both the loops. So it's after this, at the end of this double loop. If we exit this double loop without returning in the middle, it means that we checked all possible pairs of integers from S, and we verified that none of them add up to X. And so we say that we didn't find such a pair. Now the complexity of this brute force algorithm is going to be proportional to the number of pairs of integers that there are in total. Because in the worst case, we'll be checking every possible pair and we'll be finding that none of the pairs adds up to X. So in fact, whenever you have a double loop like this, for where I varies from 1 to n and j varies from 1 to n, regardless of how long, how many statements you're going to execute within the loop, you are having n different values of I and you're pairing them with n different values of j. So the complexity of this loop, assuming that this takes a constant amount of time, is going to be proportional to n square, n times n. And so the total complexity of this, the worst case complexity of this brute force algorithm is going to be theta of n squared. But the question asks you to come up with a theta of n log n algorithm. So you need to come up with a faster algorithm to solve the problem. Now, one way to speed up, one possible way to modify this algorithm to try to speed it up is by not iterating over. So for a given, let's say you choose a particular value of I. Instead of searching for all possible values of, instead of testing all possible values of the second element, why don't we just directly search for the value which will make S of I and the sum of that value add up to X. Right? So let's say that we keep the outer loop as it is. We vary I from 1 to n. But instead of trying out all possible values of j, we just search for the complementary value. So for a given value of I, for a fixed value of I, which means when one of the integers in the pair is fixed as s of I, the other integer needs to be x minus s of I if we want the two to add up to x. So we are going to search for x minus s of I in the set S. And how much time would it take to search for this value in S? Well, if we use linear search to search for a given element in S, then that's going to take theta of n time in the worst case. In which case, for every possible value of I, we're going to take time proportional to n in the worst case. So the complexity in that case will remain the same. It will be theta of n square. But what if we try binary search? What if we try to search for this element in S using binary search? Well, we can't use binary search straight away because we are not given that the set S is sorted. But if we were to sort it, we know that sorting S wouldn't take time more than theta of n log n because we have already seen an algorithm, merge sort, which takes theta of n log n time in the worst case to sort a given array. So we can use merge sort to first sort S, and then we could we could do something like this. We could pick each element one by one and test whether the complementary integer x minus the integer we have fixed is present in S or not. And if our S is sorted, okay, first sort S, assuming that S is first sorted using merge sort, this search operation is going to take time in the worst case theta of log n because there are n elements in S in total. So if each element of S is going to take time theta of n log n to check whether the complementary element is also present in S, then the total time taken by this algorithm is going to be n multiplied by log n, which will be theta of n log n. Right? So if for a given value of I, this is going to take time that is proportional to log n, or let's just worry about an upper bound. This search operation is going to take some time that is upper bounded by a constant multiple of log n, time taken to run the body of this loop. So if we run this loop n times, in the worst case, we're going to take time less than or equal to Cn log n. This means that in the worst case, the running time of this entire algorithm is going to be big O of n log n. And if in the worst case, the running time is bounded from above by n log n, this means that for any input of size n, we are guaranteed that the running time of this algorithm is not going to exceed this value, whatever it is. So it's going to lie in big O of n log n. If the worst case time is upper bounded by n log n, some constant multiple of n log n, then the running time on every input of size n is going to be upper bounded by the same number. We can also prove that in the worst case, we're going to have a lower bound of n log n because binary search in the worst case is going to take time theta of log n. This means there will exist a constant c such that this running time is bounded from below by some constant times log n. So we can run this loop n times for all possible values of I, and we'll end up with a lower bound of n log n. Uh, we'll end up with a total running time that is bounded from below by a constant multiple of n log n. And so we can say that the worst case time is big omega of n log n. But note that just because the worst case time is big omega of n log n doesn't imply that the running time on every input of size n is going to be omega of n log n. It's possible that the very first pair we test could add up to x. So we are only looking at the worst case time here when we are talking about big omega of n log n. But this applies, this big O of n log n applies to all possible inputs of size n, because if the worst case has an upper bound, then that upper bound is going to be an upper bound for all cases. But if the worst case has a lower bound, that lower bound need not be a lower bound for all possible inputs of size n. It's a lower bound only on the worst case. So the running time of this algorithm in general is big O of n log n, but in particular, if you're talking about the worst case time, we can say that it's theta of n log n. So to summarize, what the algorithm does is it first sorts the set S using merge sort, and that takes time theta of n log n. And then the algorithm runs this double loop, or sorry, it's just a single loop here where for every possible value of I, for I varying from 1 to n, you search for x minus s of I in S. And by the way, one small note here, uh, your search needs to ensure that you're not checking s of I itself. So this search is, strictly speaking, it should be in s minus s of I, the element s of I, because you don't want to pick the same element twice, right? So excluding s of I, you're trying to search for this value in the other elements of S, because one of the values has been fixed to be S of I. The other value should come from the remaining n minus 1 elements. So you may need to modify slightly the binary search procedure here to ensure that a case to ensure that when you're examining S of I itself, it's not, you're basically going to ignore that, even if you end up matching. So for example, if x is equal to 100, and if there is an element in S with a value of 50, so if you fix that element and if you search for 100 minus 50, which is 50 in S, you don't want to hit the same element twice. Right? You want to ensure that the value 50 that you're searching for is found in the other elements. If you don't find another 50 in S, then you can't conclude that uh, that you have found a pair 50 comma 50, because you can't pick the same element twice. So you need to modify your code suitably that you're not checking the same element twice. And the way you can do that is to ignore the case when you're at S of I itself. Just assume that the answer in that case is false. Or you could test the surrounding elements when you encounter another 50 in the same, when you hit the same place and you find that that's the value you were searching for, you can just search for the neighboring two elements, because if this array is sorted and if there is another 50 in this array, then it's going to be either the left element or the right element. Anyway, with that clarification, let's go back to this running time. So this is the time to sort S, and then we're going to take a further theta of n log n time in the worst case to run this loop, where you do binary search n times. For each element, you search for the complementary value. we search for um, x minus s of I in S, or rather, strictly speaking, in S minus the element S of I. So the total time taken by the algorithm is going to be theta of n log n. And if you have two functions, both of which are in theta of n log n, then their sum is also going to be in theta of n log n. And you can prove that easily if you, um, well, I'll just leave that as an exercise, but you can prove this from the definition of theta notation. You can write the definition for the theta notation here. Then, uh, uh, if this function is f of n is in theta of n log n. So um, f of n is bounded from above and below by a constant multiple of n log n. Likewise, if this is g of n, then g of n is bounded from above and below by two other constants, constant multiples of n log n. So if you add these two functions up, you'll find that you can add the constants and you can still claim that their sum is going to be bounded from above and below by constant multiples of n log n beyond a certain threshold n naught. And that threshold n naught is going to be the larger of the two thresholds that we use here. So with that, I'll leave the details to you as an exercise. But in effect, we have come up with a theta of n log n algorithm that solves this problem.